In this presentation, I will be presenting DisplayFab, a framework to support researchers and makers in the fabrication of interactive devices. In particular, exploring the current state of display fabrication and where future challenges and opportunities lie. If we define an interactive device as a device supporting input and output, can I briefly ask you to consider whether you've built such a device? And further, can I ask you to reflect on whether your design has been limited in form based on the components that you've had available? In fact, you might have ended up with a device resembling one of these fantastic projects from Instructables. These images are projects created by makers, and I'm sure you agree that they show the scope for fabricating interactive devices. However, in prototyping and production of interactive devices, continuous display components are often simulated by discrete sources such as LEDs and LED displays. In this paper, we position the strength of material-centric display fabrication against the limitation of component-based methods. We posit that material-centric fabrication promises, firstly, truly free-form output of display types, where form can be equated to function, and secondly, the potential for automated deposition of material and therefore use by non-specialists in line with 3D printing. Material-centric fabrication holds the potential to facilitate the prototyping, production, and development of interactive devices with fully configurable forms. We delineate interactive devices as being able to be thought of through the terms of input, output, and control. In this work, we argue that the biggest bottleneck in developing truly free-form interactive devices are the display elements, the output elements. Material-based methods for exploring input are well explored and can be argued as converging, for example, incorporating capacitive touch through electrically conductive surfaces. We argue that control is circumventable and unfeasible as an approach for material-centric development. Power and logic can be effectively decentralised from the interactive device itself, and we don't need to recreate the strengths of microcontroller and battery technology. However, output methods are diverging in material, fabrication method, and support. Here are examples of what can be done by you as a maker through material-centric display fabrication methods. There are a wide range of inspirational work on material-centric display fabrication within human-computer interaction. As part of this paper, we carried out a targeted literature review focusing on 19 core contributions that are displayed here. Specifically, these works range over 5 key display materials and a range of different fabrication methods. These works are diverging. This creates the need for reconvergence in order to outline the challenges and opportunities simultaneously for both researchers and makers. We introduce this paper, DisplayFab, as a contribution towards remedying this divergence. This paper is a framework that is built on existing work through a targeted literature review and can act as a roadmap for future research. We identify the need for a unification of vocabulary and challenges across display fabrication works, as well as a greater emphasis on appropriate comparative measures within research. As part of the derivation of the DisplayFab framework, we formally define what we mean by this term DisplayFab. Firstly, DisplayFab focuses on personal fabrication, encompassing empowerment of makers themselves and a focus on domestic and semi-domestic settings and maker spaces. Secondly, we define DisplayFab as particularly focusing on electronically addressable visual displays, so a focus on displays that can be adapted based on digital signals and that provide visual output to the user as the most common way of performing digital output. And thirdly, we focus on the deposition of active display materials, so specifically adhering to the tenets of additive manufacturing and 3D printing through deposition of homogeneous malleable materials. This definition and these 3 key areas provide us inclusion and exclusion criteria for the framework itself. As well as implementing a framework to support challenges and opportunities, DisplayFab aims to support makers in design choices when using these active materials. The divergence of materials and methods is justified by a wide range of display material properties and the usability of fabrication processes that are suited to different use cases. Direct comparison is currently limited between individual pieces of work, and through this chart we push the need for unification of measurement and reporting not only for researchers but also for makers who may be addressing these particular materials. DisplayFab itself is derived from the seminal 2017 Personal Fab framework by Patrick Bowdiche and Stephanie Müller. This framework provides categorization through which to explore all of personal fabrication through the key frames of hardware, software and user, and society. DisplayFab acts as a subsection of personal fabrication. However, we argue that it must be handled independently. Through a targeted literature review, we identify 4 breakpoints when it comes to applying the original Personal Fab framework to display fabrication. These breakpoints are identified due to 3 factors inherent to DisplayFab. Firstly, the complexity of display tech and active display materials. Secondly, the early stage of development of these materials and fabrication processes themselves. And thirdly, the need to incorporate design for interaction in a way that isn't necessarily inherent to all of personal fabrication. The first breakpoint that we introduce is over material and deposition, centered around the lack of bespoke tools for display fabrication. This causes a reliance on reappropriating existing craft and fabrication tools, as well as inherent structural complexities. The second breakpoint identifies breakages in how domain knowledge is handled, with DisplayFab's early stage of development and integrated design for interaction requiring novel approaches. The third breakpoint highlights how feedback loops must be redefined from Personal Fab to DisplayFab due to its centering around handheld processes and the development of functional outputs. Lastly, for the fourth breakpoint, the categories under society are reworked in the context of DisplayFab from Personal Fab. This is specifically from its sustainability and intellectual property issues, which are adapted in their reapplication to DisplayFab, but extended to include core issues of health and safety to users and ethical impact of creating displays. Having driven these 4 breakpoints by the needs of DisplayFab, we then take these 4 breakpoints and we use them to restructure a new framework, providing the categories for the DisplayFab framework itself. We use these breakpoints to isolate the uniqueness of display fabrication challenges and to synthesize a new framework based on these 4 sections. We focus challenges and opportunities around 1. Material and deposition, 2. Conception and software, 3. Feedback and interactivity, and 4. Responsible innovation. This forms the core of our contribution, a new framework and roadmap for display fabrication. Specifically in creating the roadmap and our forward-facing side of the framework, we identify 30 core challenges and opportunities for further development and research into material-centric display fabrication. These are developed around the core 19 HCI research papers explored within the targeted literature review, as well as incorporating literature from further afield and further research opportunities, for example, from material science, industrial sources, and electronic engineering. Within the first category of our framework, material and deposition, we explore material challenges, so how makers engaged with display fabrication can explore new active materials. We also consider automation in line with freedom of form of display fabrication elements and output artifacts, as well as use by non-specialists. And lastly, we explore access to non-specialist makers, specifically enabling early adopters and exploring the intersections of maker culture and those who might use such systems. In the second category of the framework, conception and software, we explore challenges and opportunities relating to what design and learning looks like for the complex subject of DisplayFab. For example, how can we develop interventions and computational tools to support DisplayFab accurately? How do makers and ourselves learn adjacent to understanding active materials? In the third category of DisplayFab, we look at feedback and interactivity, specifically focused on where people intervene within a system. In this context, we consider challenges and opportunities relating to the development of tools regarding interactive fabrication, a concept developed in the context of personal fabrication, as well as exploring and appropriating testing structures specific to display materials. An example of a challenge in this area is how we develop unified and transferable testing structures between different materials and different structures, as well as between different fabrication processes. In the fourth and last category of the DisplayFab framework, we explore the concept of responsible innovation. Specifically, we ask how these technologies fit into the world today and what challenges align with this concept of responsible innovation and development of technology. How is ownership of material and information managed when displays and interactive devices themselves can be fabricated configurably and on demand? The key question of sustainable development and how we develop sustainable fabrication processes in order to produce interactive devices. And lastly, the question of how makers and users can be protected, both physically through health and safety considerations, but also ethically in the context of malicious use, passive impact, and who the maker and the user actually are. We aspire that this contribution, the DisplayFab framework, will support the convergence and concentration of DisplayFab methods and research, and as a result, it will unlock further steps in the personal fabrication of free-form devices. We hope that this framework can be used to bridge the gap between research and makers, increasing adoption and implementation of material-centric display fabrications. Specifically, this will enable us as a community to work towards the vision of on-demand, configurable, free-form interactive devices with forms custom to their use. Thank you very much for listening.